Okay, now we're going to take a look at a different one, and I'm going to show you another advanced option. Now, the advanced option is not something that you would have used on the last lab anyway, because the video that I provided for you, it wouldn't have worked very well. This time, we're going to take a look at a video shot in high speed. In other words, we're not going to have near as much of that motion blur that we saw in the first one by dropping the little puck, where it got smeared out when it started moving really quickly. I have another feature on my camera where I can do high-speed video that actually cuts down on that a lot. The downside is you're going to end up, well, arguably it's not a downside. The upside is you get a whole bunch of additional frames, but that could equate to having to click on a whole bunch of things. Luckily, Tracker has a feature built into it that as long as you have something that you're looking at that is noticeably different from anything else in the picture, it can do an auto track. So we're going to show you that. All right, File, Import. We're going to bring in the video for this one. You can go to, if you're on this computer, desktop, we're going to go to the Tracker Labs, Lab 3B, and import the video that I have there. I will also be uploading this one where you all can get to it. But this one, when we bring this up, real quick, let's take a look at it. I hit play. We can see my hand over here. There's a meter stick that is taped to the wall in the hall. Now, we can't read the individual parts of the meter stick, but that's okay because we can see the entire meter stick, which is the point. And I toss an orange ball that goes flying through the air. Goes up and comes back down. Now, you don't necessarily need to track the entire thing, but I do want you to begin as it's on its way up. In fact, I'm going to try and find a point where it has left my hand. Here we go. It's leaving my hand. We'll call that frame 90. It's clearly out of my hand by 89, so frame 90 is a good enough place to begin. And I'm going to drag this over. It'll go up. I want it to come back down. I'm going to have it come back down over on the far side. We could call it frame 170. So I'm going to trim this from 90 to 170. And if you'll notice down here in the frame rate, instead of 30 like we saw last time, this is actually 119.45. It's 120 frames per second, which means this slows everything down by a factor of 4. It's 4 times slower. Now, if we watch this in real time, it would be moving in slow-mo 4 times slower than usual. Now, this isn't one-dimensional motion, and that'll come into play here in just a moment. Let's go ahead and teach it how long a meter is. I apologize. This is why it's useful to have an entire meter stick in the frame so you don't have to read the individual parts of the meter stick. You can just drag it from one end to another. Looks good. I'm going to hide that. And I'm going to set up my coordinate system. Now this time, since we're dealing with 2D motion, I can't really set things up where all the motion is happening in one direction like last time where I dragged the axis around. So hopefully my camera is pretty level. We're about to find out. If not, then it should be pretty close. We're going to find out when we actually see our outcome. All right, I'm going to hide my coordinate system. This time I'm going to put it on the dead center of the ball because I'm going to try and track that. Okay, so we've got everything set and ready to go. I'm going to go to Create, Point Mass, and this time, pardon me, instead of holding down simply Shift, Shift brings up a square crosshair. I'm going to hold down Control and Shift, and you will see a circular crosshair. Then I'm going to try and click on a very clearly identified part of the ball. I think what I'm going to do is I'm going to click over here where the orange goes into shadow, so it's kind of on the edge there. It's going to bring up a new screen. Basically, it says Template. That's what I've clicked on here, and this is what the pixels look like close in. And what it's going to do when I click Search is the computer will automatically go through every frame and find the closest match in pixels to our template. So if our template, wherever you click, is something that looks noticeably different than the rest, then it should track just fine. The problem is, with it being a computer, it can't think, so sometimes it gets confused and starts tracking something completely random. Hopefully that won't happen, but we're going to watch it as it goes. I like to drag the screen back over here where I can kind of see it, but I can clearly see what it's tracking. So here we go. I'm going to click Search, and let's see what it does. The ball starts moving and it auto-tracks, and it's doing a wonderful job of it too, at least thus far, knock on wood. It seems to be following the ball pretty much exactly where we need to. Now it's going to fluctuate a little bit, may not get it exactly on the same spot on the ball each time, but let's hope that it mostly follows the ball. Over here you can see in our position versus time for the x, we've got kind of just a straight line, which is actually what we're after. Looks like it's done. Hooray! So we managed to get a clear track. If you ever see any of the dots go off somewhere else, it means that the computer got confused and it found something else that matched better to its template. Again, computers can't think, they can only basically do what we tell them. So sometimes you may have to come down here and say, yes, that's a good track, or no, you're bad at this, etc., etc. Most of the videos that I put together, I try and do a good job of making certain that there isn't the chance that the auto track will lock on to something else, but I can't make any promises. Part of it can also depend on where you click on the ball. So if you run into a problem, just kind of backtrack and then try it again. See if you can click on a spot that's more noticeable on the ball. All right. All of that is good, so I'm going to click close. This is looking wonderful. Now, what we've got here is our x position versus time, and it is a straight line. That's actually what I'm after. In two-dimensional motion, one of the big things that we work with is we assume that there is no acceleration in the x direction and that there is a constant acceleration in the y direction. Well, this is a position versus time graph, and we have a constant slope, so that means we should have a constant velocity. And if we have a constant velocity, that means our acceleration is equal to 0. This is actually exactly what I want you to generate for our position versus time in the x. Now for the y, we don't have a constant velocity, we do have an acceleration. So what that means is we're going to end up with not a straight line, but a curvy line. In fact, that's what we get. Here's my y coordinate as a function of time. It goes up and then it comes back down and we have a curvy line. In fact, we're also going to look at this to see if we can find the acceleration due to gravity. All right, now down here, we actually have motion in both the x and the y. I'm going to highlight all of them just as we've done before. I'm going to right-click, copy cells. We'll go ahead with full precision. Why not? And then I'm going to open up Excel. All right, get a blank worksheet. I'm going to paste those in, and now we've got all of our data. A whole bunch of it, too. We've got 82, about 80 data points, maybe 81. So that's a lot more than we would normally be able to collect. That's one of the upsides of working with Tracker and a video recording. We can get a lot of data points, which is really, really nice. All right, let's see. Insert graph. I want you to make two graphs this time. One of them is going to be the x direction, select data, so add. And I'm going to call this position versus time x. And then we could put in here Sanchez, my name. Put in your name when you do this so I know whose graph this is. X position, well, our x coordinates are supposed to be our time, so I'm going to come in here and I'm going to left click and drag all the way down to collect the times. There we go. And then my y, now be careful, it's not guaranteed to be y. What y means is my horizontal. On this first one, it's the position versus time for the x direction. This is my horizontal. Okay, so I've got that. Click done. And there we go. There is that graph that we saw before. This is our position versus time graph. It is a nice straight line, which means it has a constant slope, which means our slope, add trend line, display equation on chart. I still want that. But the slope of our position versus time graph should give us the velocity, and this has a constant velocity. In fact, now we have a measurement. Our position is our y, our horizontal, or I'm sorry, our vertical, sorry. Our slope is 3.24 times x, our horizontal. So once again, take a look at the video that we've looked at before, but this is y equals our slope times x minus our y-intercept, which is almost 0 in this scale. You can see that it basically goes through 0, 0. So our velocity, we've made a measurement of our x velocity. It is 3.24 meters per second. Great. I'm going to go through and I'm going to clean up this graph too, but first, let's go ahead and make the second graph. Well, actually, no. Let's do this the quick way, or the smart way. Let's go through and clean up this graph, and then I'll show you a trick that might save us a little bit of time. So let's go over to, it's been a little bit since I was actually working with it. Nope. There we go. So the last little option over here, axis options, number. We're going to go from scientific. I'm not a big fan for that right now. Ooh, this actually looks pretty good, although I think we'd be fine doing one decimal place. Okay. Pardon me. And then over here, we're going to clean this one up. Format axis. These options. Let's go away from scientific notation once again. And that looks pretty good. I would go ahead and leave the 2 decimal places just because it makes it a little bit easier to see. One of the other things that you can do, vertical axis crosses. Let's see if this is the correct one that I'm actually looking for. Let's try negative 0.5. No. Sorry, it's the other one. Okay, so I'm going to come out over here. I'm going to format axis. I'm going to cross this value at negative 0.5. There we go. You can change down here. Horizontal axis crosses the vertical axis at axis value. There's an automatic where it tries to put it wherever. You can actually adjust that and move it down a little bit. So you can see I moved my horizontal axis where the numbers are down to the bottom of it. And that's perfectly fine. Okay. You could also go through and probably remove the negative 0.5 and just start it from 0. Now that I look at it, that might be a good option. Anyway, not terribly important. The last thing that we need on this to make it complete is back up over here. We're going to go to Chart Tools, Design, Add Chart Elements, and we're going to go with Axes Titles. So I'm going to go horizontal, and this is time in seconds. So I'm going to go ahead and mark the units that it's in seconds. And then I'm going to click outside of that. Let's go Add Title, Axis Title, Vertical. And this one is our position in meters. Now you can also put position in meters or x meters, but in my graph title, I've got position versus time in the x direction. Here's where we might be able to save some time. You could go through and you could recreate this the exact same way, or left click on this, copy it. You can either go here like this, copy, or Control C. Click outside of the graph. Always remember to do that, because if you don't click outside of the graph, it tries to paste the graph in the graph, and it just gets weird. It's like Inception. Anyway, then out here, then you do a paste. Great. Now that we've got a copy of it, let's change this one. All right, here we go. So what I'm going to do is I'm going to change my data. So I left click on the data to select it, then right click and go to Select Data. I'm going to do Edit. We're going to change the name of this to the Y direction. Now my X values are going to stay the same because the time is still the same, but my vertical axis, I now want it to be the Y direction. Okay, so I'm now selecting my Y data points for my, hey, look at that, Y axis. Great. So instead of redoing the graph entirely like we did the first time, I can copy that graph. Here's one of the problems though. Our trend line looks a little wonky, to say the least. Okay, left click on your data, right click on it, and go down to Add Trend Line. Now we've got linear, but this isn't a linear fit. Well, we could do logarithmic. Didn't like that. Okay. So, properties. Nope, that's not what I wanted. Sorry, right click, go back to trend line. Sometimes if you try and get it to calculate something and it says bleep blorp cannot calculate, let's try moving average. Didn't like that. Okay, let's try polynomial second order. Strange, I'm not seeing it clearly. Hang on just a second. I'm going to go in the old trend line, I'm going to select it, and I'm going to delete that. Okay, now I'm going to select my data. Oops. Format trend line. There's a trend line there that we can't see. There's a polynomial second order, which is actually what we're looking at. Display equation on chart. Now the reason we can't see it is because it's agreeing with our data really, really well. I'm going to bring our equation line up here and move my chart title over some so I can see that, and then see if I can clean this up some. Chart type, select data. We could also format trend line. Okay. Chart styles. No, I think that'll be good. We know that the best fit line is there because we've actually got the equation for it. Let me see if I can do format trend line, and then let me see if I can do something with the colors on it. Color. There we go. Now we can see it in red in that little bit of contrast. You don't need to worry about that too much. If I can see the equation up here, I know that the trend line is there. And you certainly don't need to print this in color. That's totally fine. Color's very expensive. All right. In short, these are the two graphs that I'm actually looking for. You can do what we did before and paste them into PowerPoint if you'd like. If you're doing this on this computer, you can actually do Save As and then go into, not student data from Lab 02, but we could do Browse. It'll be just a moment. Desktop, Tracker Labs, Lab 3B, and Student Data. And I'm going to do 2017. E.S. Sanchez, and I'm going to do Lab 003B. Now I've got that saved there, and then you could turn around and send me an email later on to let me know where it's at. Now, in just a moment, I'm going to bring up another video to explain what we're looking at. We've got these two graphs, one of which is the position versus time in the x. We can see that it's a straight line, and therefore we have no acceleration. We have a constant velocity, and the slope of this line should actually be our velocity. We know that that's 3.24 meters per second. Now, the one that's a little harder to understand is our position versus time in the y direction. I'm going to make a short video and try and connect that to this that explains what you're looking at there and what our conclusions can be. Before we switch over to that, we have an equation that says y equals negative 6.0 times x squared plus 3.77x minus 0.02, something that's pretty close to 0. We're going to see what that comes into in just a moment. As a reminder, our y here is actually our y position, so that's convenient, and our x is actually time. So what this should say is delta y equals negative 6 times t squared plus 3.77 times t minus about 0. Okay, so let's talk about interpreting the second of the two graphs. Now, the first one, the horizontal one, we've already talked a little bit about. It's a straight line on the position versus time graph, which tells us that the velocity is constant and that the slope of it was our velocity in the x direction. Not only is it our initial velocity, but it's also our final velocity. And that should be a pretty good indicator that our acceleration is actually equal to 0. You're welcome to double check. Let's take a look at the second graph. Now, I've gone ahead and set up exactly what we'd be working with for the y direction. As you've learned in class, we split things up, what's happening in the x direction, what's happening in the y direction. Now I've got my position, displacement in the y, equals my initial velocity in the y plus t plus 1/2 ayt squared. So that's all of this is set up for the y direction. Now, one of the things you may be thinking is, why didn't he have me linearize the graph? Well, that's because this one won't actually linearize in the same way that the last one did. Now, the last one relied on the initial velocity being 0, and then that made that middle term disappear, and then we could linearize it. Now, if we do delta y versus t, then we won't get a linear graph, but if we do delta y versus t squared, we also won't get a linear graph because this middle term has a t dependence, and it will actually mess with it some. You're welcome to give it a try, but it won't linearize very easily, and that's why it was important to only drop the object in the last one. That being said, we can still get really useful data from this, we just need to know what we're looking at. So here's my equation. Delta y, my displacement in the y, will be equal to my initial velocity in the y times time plus 1/2 acceleration in the y times t squared. Now we expect the acceleration in the y to be about that of gravity, so it'll be somewhere close to negative 10 meters per second squared. But we'll find out. Okay, let's see. So let's take a look at what we've got. As I said, the initial velocity is not equal to 0, so that term doesn't disappear. I'm going to do something weird. I'm going to take this term with the initial velocity and the term with the acceleration, and I'm going to swap them around. Okay, so now it's the same equation, but I've got my position in the y, my displacement in the y, I should say, equals 1/2 a sub y times t squared plus v naught times t. Now remember, the equation that we got for our best fit was our y, our vertical value was equal to some number times x squared plus b, some other number, times x, plus c, some other number. I've copied over what we actually got from the graph. It said that the best fit was y equals negative 6.0 times x squared plus 3.77 times x plus a number that to three significant figures is actually 0. Here's where we're going to bring this back in. Remember what I just showed you. Delta y also equals 1/2 a sub y times t squared. Well, in my graph, the horizontal value is t, so this is t squared, plus some value times t, my horizontal, plus there should be a plus 0 over here, but that's actually my initial position. What we do is we subtract it over here, and so we have y final minus y initial, which is, wait for it, delta y. Delta always means final minus initial. The way we study them in here, we actually combine them both into a delta y. In this case, delta y will equal my y position because we set our origin there at the very beginning. If we didn't, then delta y would just factor in that we didn't start at 0. The important thing is this. This value is 1/2 of our acceleration in the y, at least what we've got from our video, and this value is our initial velocity in the y. Now our velocity is going to change as time goes on because it slows down, slows down, slows down until it comes to a stop at the apex, and then it starts speeding back up again, but this is our initial value. Okay, so now that we've got those laid out, all of these are actually the same thing, just in different ways of looking at them. All right, so now what that means is 1/2 of our acceleration is equal to negative 6.0. If you double check the units, you'll find that it has to be in meters per second squared, and we'll find that that means that negative 6.0 is about 1/2 of our acceleration, so we would measure it somewhere in the negative 12 meters per second squared range. A little high, but that's okay. It's still in the ballpark of what we're looking for. And our initial velocity, we get a measurement of 3.77 meters per second. So now we know the initial velocity in the y, and we know the initial velocity in the x. We could even go so far as to work backwards and find the angle at which it leaves my hand using vectors. But that's a little bit of understanding of what that best fit line that you just got actually tells you. It's once again a measurement of the things we're looking for.